Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the concept of the curl in the vector field and we will also learn about the Stokes theorem. So in the previous video, we learned about the concept of the divergence and we have seen that this divergence represents the net outward flux of the vector field from the given point. So basically, it tells us that whether the vector field acts as a source or the sink. So similarly, the curl represents the net circulation or the rotation of the vector field around the given point. So we have seen that the divergence of the vector field represents the scalar quantity, but unlike that, the curl of the vector field represents the vector quantity. And this curl of the vector field points along the axis of the rotation, and we can find its direction using the right hand screw rule. So mathematically, the curl of the vector field A can be given as del cross A, where this del represents the vector differential operator. So now, let us see the actual definition of this curl. So before we see that, just recall that earlier we have seen that the line integration around the closed path is called the circulation. And this circulation gives us the net circulation of the vector field around the surface that is covered by this closed path. So let's say the area that is covered by this closed path is equal to delta S. So as per the definition of the curl of the vector field represents the circulation of the vector field around the given point. That means if we divide this closed loop line integral by the surface area, then we will get the circulation per unit area. And as this area tends to 0 or it becomes infinitesimal small, then that represents the circulation around the point. And as I told earlier, the direction of the curl is along the axis of the circulation. So basically, it is normal to this surface area. So this curl is also represented as the del cross A. And we know that the cross product of this del operator and the vector field A can be found using the determinant. So in this way, if the vector field is given to us in the Cartesian coordinate system, then we can find the curl of the vector field using this determinant. Similarly, if the vector field is given to us in the cylindrical coordinate system, then the curl of the vector field can be defined like this. Likewise, when the vector field is given to us in the spherical coordinate system, then the curl of the vector field can be given by this determinant. So in this way, in the different coordinate system, using this determinant, we can find the curl of the vector field. So now, let us see some of the properties of the curl. So this curl follows the linearity property. That means the del cross A plus B can be given as this del cross A plus del cross B. Likewise, when we have the scalar and the vector field together, then the product rule can be applied like this. So as you can see, this rule is very similar to the differentiation rule. That means one time this del operator is applied to the scalar field and the second time it is applied to the vector field. Similarly, if we find the curl of the gradient, then that is equal to 0. So to be precise, we can say that the curl of the gradient of the scalar field is equal to 0, where this phi represents the scalar field. And likewise, the divergence of the curl is also equal to 0. So to be precise, we can say that the divergence of the curl of the vector field is equal to 0, where this A represents the vector field. So these two properties are very important properties and we will discuss more about it at the later part of the video. So likewise, the curl of the cross product can be given by this expression. So these are the some of the important properties of the curl. So in general, we can say that the curl represents the measure of the circulation around the specific point. Or we can say that this curl tells us that how much the vector field curls around the specific point. So from the definition of the curl, we can say that this integration of the A dot dl is same as the surface integral of this del cross A times ds. So this theorem is known as the Stokes theorem. So we know that the curl of the vector field gives us the circulation or the rotation around the infinitesimal small point. While if we see the Stokes theorem, then it gives us the circulation of the vector field around the specific area. So as per this theorem, the circulation of the vector field A around the closed path L is equal to the surface integral of this del cross A over the open surface that is bounded by this L. So we already know that the line integration around the closed path will gives us the circulation. But now let us also prove that indeed that is equal to the RHS. So let's say we have some surface area S, and for simplicity we are taking the rectangular area. So now let us divide this area into the n number of segments, and here the n is the very large number. So here as this n tends to infinity, then the area of the each cell is also infinitesimal small. But here for the simplicity it is shown little bigger. So here if we take the any cell K, then its surface area can be given as this delta as K. And here let's say the path that is bounded by the surface area is equal to Lk. So here for the each individual cell we can say that the closed surface integral or the circulation is equal to integration of A dot dl. And here this integration is taken over the specific closed loop Lk. So here if we perform the summation of the each cell, then we will get the overall circulation for the given surface S. So now in this expression, if we multiply and the divide by the delta Sk, then the equation will remain the same, right? So here if we consider the left hand side, then it represents the summation of the circulation of the individual cell. So here if you consider the any two adjacent cells, then their interior path will get cancelled out. And effectively, this overall summation is the line integral over the outer path. So that represents the circulation or the rotation around the given area as. That means the left hand side is equal to the integration of A dot dl over the outer path L. Now on the right hand side if you see, then as per the definition of the curl, as this delta Sk tends to 0, then the summation will become the integration. And therefore this term is equivalent to the del cross A, and here this delta Sk will become the differential area. And in this way we are getting this expression of the Stokes theorem. That means the curl gives us the circulation around the given point, and if we integrate it over the specific area, then we will get the net circulation around that open surface. And that is same as the line integration around the boundary of that surface. So that is the meaning of this Stokes theorem. So using the divergence and the curl alone, of course, we cannot define any vector field completely. But whether the divergence or the curl of the vector field is 0 or the non-zero, from that we can get to know about the specific characteristic of the vector field. So for any given vector field, whether its curl and the divergence is 0 or non-zero, in that regards we have the 4 different possibilities. One is its curl and divergence both are 0. Second is the curl of the vector field is 0 while the divergence is non-zero. Third is the curl is non-zero while the divergence is equal to 0. And the fourth is both curl and the divergence are non-zero. So if you see this vector field, then this represents the first case. Because in this vector field if you see, then at any given point, the incoming flux is same as the outgoing flux. Therefore, the divergence of this vector field is equal to 0. And here, since the field is not rotating, so its curl is also equal to 0. Similarly, this vector field represents the second case. So for this vector field if you see, then the divergence is non-zero, because here the vector field is converging at the specific point. That means here this divergence is non-zero. But here since the field is non-rotating or the circulating, so we can say that its curl is equal to 0. So this field represents the second case. So likewise this vector field represents the third case. So in this case if you see, then the field is rotating around the specific point. Therefore, its curl is equal to non-zero. But since this field is not either converging or the diverging, so its divergence is equal to 0. And likewise, if you see this fourth field, then for this field, both divergence and the curl are non-zero, because this vector field is both circulating as well as the diverging. Therefore, for this given field, the divergence and the curl both are non-zero. So in this way, for any given vector field, whether its divergence or the curl is 0 or not, from that we get to know about the specific characteristic of the vector field. So for example, if the divergence of the vector field is 0, then the field is called solenoidal. So as per the divergence theorem, as you know, if this del dot A is 0, it means that this term is also equal to 0. That means if the vector field is solenoidal, then its closed surface integration will also become 0. So earlier we have seen that the divergence of the curl of the vector field is always 0. That means whenever this del dot A is equal to 0, then this solenoidal vector field A can be represented by the any other vector field F by the following expression, where this F also represents the other vector field. So we can say that whenever the vector field A is the solenoidal, then these two conditions are always true. So similarly, if the curl of the vector field is 0, then the field is said irrotational. That means whenever, for any given vector field, if the del cross A is 0, then the field is said to be a irrotational. Now as per the Stokes theorem, we have seen that if this del cross A is 0, then we can say that the integration of A dot dl is also equal to 0. Moreover, earlier we have seen that the curl of the gradient is also equal to 0. That means whenever we have the irrotational vector field A, then it can be always expressed in terms of the scalar field. But in reality, here we will also have the negative sign. That means whenever we have the irrotational vector field A, then these two expressions are always true. So in this way, using the divergence and the curl, even if we don't know about the exact field equations, then also we can get to know about the sum of the characteristic of the vector field. So I hope in this video you understood the concept of the curl as well as the Stokes theorem. So in the upcoming videos of the electromagnetics, by using the key concepts of the curl and the Stokes theorem, we will understand the concept of the Faraday's law as well as the Ampere's law. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.